A planet just whispered across the void. Not with a radio transmission, not with a blinking light across a telescope's field, with a chemical fingerprint carved into starlight itself from a planet 124 light-years away. If the analysis holds, something out there is making a fragile gas that shouldn't linger unless it's constantly replenished. On Earth, the only thing that does that is life. The planet is called K2-18b. It orbits a cool red dwarf, a small sun that glows more softly than ours. When astronomers turned the James Webb Space Telescope toward it and sifted the faintest colors of light passing through its sky, they saw hints of a molecule that on Earth comes almost entirely from ocean life, dimethyl sulfide. Later observations strengthened the case. Not proof, not a verdict, but a signal strong enough to sit around the 3 sigma mark, roughly 99.7% confidence that the feature is real under the models used. Far from a fluke, still a long way from certainty. Exactly the kind of tension that makes scientists lose sleep. If K2-18b is truly exhaling a life gas, it could be the most promising sign of biology we've ever seen beyond Earth. And if it's not, it will teach us how to stop fooling ourselves and finally catch the real thing. Either way, tonight we're crossing a line, from silence into possibility. Imagine the first humans who learned to read footprints. At first, sand was just sand. Then someone noticed patterns and realized something alive walked here. Astronomers are trying to do the same with light. As K2-18b passes in front of its star, a thin ribbon of starlight filters through the planet's atmosphere. Gases in that air grab very specific colors. Tiny gaps appear in the spectrum, like missing teeth in a comb. Match those gaps to a molecule's known fingerprint, and you learn what the air is made of without ever going there. It's elegant, it's merciless, and when the pattern points to dimethyl sulfide, it raises a very simple question with a very complicated answer. What could be making it? On Earth, dimethyl sulfide, DMS for short, is a scent of the sea. Microscopic life in our oceans produces it. Winds lift it from the waves. Sunlight and oxygen tear it apart in days. It cannot just hang around, it must be replaced. That's why scientists get excited. A fragile gas is a moving target, not a museum piece. To see it, you need a source. On a planet, a source big enough to matter implies a process big enough to change an atmosphere. Here at home, that process is life. But there's always a twist. K2-18b might not be Earth-like beneath its clouds. Its measured size and mass put it in a murky category between super-Earth and mini-Neptune. Many models point toward a Hycean world, an ocean planet wrapped in a hydrogen-rich sky. In such a place, the upper ocean could be temperate, but the deeper layers might push into strange regimes where water becomes supercritical, behaving like neither liquid nor gas. Temperatures and pressures there could challenge our intuitions. If the atmosphere is thick enough, the surface, if there is one, could lie under depths no submarine we've built could survive. So when we ask whether life could make DMS there, we're also asking what life means in a place like that. Here's where the story gets stranger. A hydrogen-rich atmosphere doesn't just change climate, it changes chemistry. Sunlight is redder around a cool dwarf star. Ultraviolet light carves different pathways. Reactions that are rare on Earth might dominate there. Could exotic non-biological chemistry make DMS in the quantities inferred? Some researchers argue we need to rule that out with specific, testable mechanisms before we invoke biology. Others point out that appealing to unknown chemistry is a placeholder, not an explanation. If we want a non-life route, we have to show exactly how the atoms dance and whether they dance fast enough. This is not the kind of argument that gets settled by opinion. It gets settled by more data, better models, and a willingness to be wrong on the way to being right. If you're fascinated by that climb, from a tantalizing hint at 3 sigma to the kind of confidence history demands, you're in the right place. Because this is how discoveries really happen, not with a single headline, but with a staircase of careful steps. Let's rewind to how this particular staircase began. A decade before Webb, the Kepler Space Telescope, reborn as K2, sniffed out a dip in starlight from a faint red dwarf in Leo. Something passed in front of the star every 33 days, dimming the light by a small but steady amount. Follow-up observations with Spitzer refined the orbit. Ground-based measurements pinned down mass. K2-18b was biggish, around 2.5 times Earth's radius and several times its mass, and it lived in its star's habitable zone, the range where starlight could keep water liquid if other conditions cooperate. Then Hubble found water vapor in the atmosphere, and the word Hycean started to appear with more confidence in papers and press releases. A planet with deep oceans under a hydrogen sky. No palm-fringed beaches, no continents, just a global sea. But a sea can be a home. On Earth, life began in water, and the simplest metabolisms don't care about sunlight. They eat chemistry, hydrogen, methane, sulfides, sourced from rocks and heat and gradients. Hydrothermal vents thrive in darkness. The question is not whether life can exist without a blue sky. It's whether the upper layers of a Hycean ocean could offer niches where temperatures are kind, nutrients circulate, and a thick atmosphere protects fragile molecules from being cooked to death. If such layers exist, they could be alive with microbial chemists. In a twilight that never quite becomes day, organisms might sense vibration and chemistry rather than color. Some could glow to communicate or lure or scare. Others might build tough outer shells from polymers we haven't named yet. And collectively, in numbers far beyond anything in our seas, they might breathe out gases that become visible to distant telescopes as faint dents in the spectrum. Of course, there's a different picture. A mini-Neptune with no true surface, a deep hot envelope where water, if present, is steam and supercritical soup, not an ocean at all. The truth hides in details: how much ammonia dissolves in water and thus stays out of the air, how clouds form and where haze sits, what the temperature profile does from top to bottom. Absence of ammonia supports the ocean idea because ammonia likes to dissolve, but that absence isn't a smoking gun by itself. Every clue arrives with caveats. That's science, not failure. Then there's the elephant in the room, significance. 3 sigma is big for a hint. In particle physics, 5 sigma, the 1 in a million false positive rate, became the gold standard because noise and bias have a habit of wearing fancy disguises. Astrophysics borrows the same caution when the stakes are huge. 99.7% sounds like a near certainty. In practice, it means the feature survives many of the ways you could be fooled, but not yet all of them. That's why Webb matters so much. Different instruments, different wavelength windows, different systematics. If the same fingerprint keeps showing up, confidence grows. If it fades with better calibration, we learn something just as valuable: what to stop trusting next time. If you've been waiting your whole life to watch that confidence meter inch upward, consider this your invitation to follow it with us. Because the next pass of data might nudge the needle, and the one after that might lock in a pattern of gases that's extremely hard to explain without biology. Or it might close the case in the other direction and teach us humility. Either outcome is a win if we keep our eyes open. Still, K2-18b isn't the only world-whispering possibility. Just 12.5 light-years away, next door in cosmic terms, Teegarden B circles a dim red star. It's almost certainly tidally locked, one hemisphere forever day, one forever night. But between them lies a ring of endless dusk, where temperatures could settle into the just right lane. Imagine standing in that twilight belt. To your left, a horizon washed in permanent sunset. To your right, a horizon of unbroken stars. Over your head, a sky that never changes much, a wind that knows only one direction, and a climate clinging to a narrow corridor between fire and ice. If life loves gradients, that ring is an invitation. 300 light-years farther sits Kepler 1649c, a red-lit cousin only a hair larger than Earth. It probably shares the same tidal lock fate, which sounds like a death sentence until you remember how stubborn life is. On our planet, bacteria thrive in boiling vents and frozen deserts. In a terminator zone, the permanent border between day and night, oceans might stay liquid. Temperatures might hover in the livable range. Gravity would feel familiar. The sky would not. Every color would be shifted toward crimson. Shadows would be strange. The star would hang in the same place forever. At around 100 light-years, K2-18b circles a surprisingly calm red dwarf. Many of these stars spit flares that strip atmospheres and erase hopes, but this one is quiet. The planet gets a little less light than Earth. Give it a modest greenhouse effect, and you could end up with conditions you'd call cool but comfortable. Depending on how its orbit evolved, it might avoid full tidal lock and keep something like a day-night rhythm. Stability is a gift. When you're looking for habitability, calm skies matter as much as distance. We hold these worlds in our minds not because we know they are alive, but because they give us laboratories to test ideas. What does climate do at the Terminator? How do atmospheres survive or fail under relentless red light? Which gases are biosignatures, and which are the clever imitations of non-life? Each planet becomes a thought experiment. The universe is running for us at full scale. Now for a change of pace, because the universe refuses to be sensible. Consider JWST-76b, a planet so hot on its day side that iron becomes vapor. Winds race the metal through the sky, and on the cooler night side it condenses and falls as molten rain. Weather there isn't clouds and drizzle, it's metallurgy from orbit to horizon. Somewhere out there, a sunset means glowing red droplets sliding out of the dark. Then there is PSRJ 1719-1438b, a world that seems to be the crystallized carbon core of a star stripped down to its heart. A planet-sized diamond circling a neutron star. Beauty born from violence, glinting in a place where light itself gets tangled by gravity. You could call it treasure, but there's no one to spend it. JWST-107b is a joke the cosmos told us to keep us humble. A gas giant so inflated and low density that astronomers nicknamed it the marshmallow. It challenges our ideas about how heat moves, how cores grow, and how atmospheres puff up. If you could stand on it, which you can't, you might feel like you're pressing your hand into a cosmic pillow. JJ1214b is a water-rich super-Earth with an atmosphere that pushes water into supercritical states, where the neat categories of liquid and gas lose meaning. Think of an ocean that is not an ocean, a steam that is not steam, a physics playground. Not cozy, not Earth, but a reminder that chemistry writes in more fonts than our planet learned to read. And J1407b, a giant wreathed in rings that would put Saturn to shame many times over. 30 colossal bands stretching distances that dwarf our moon's orbit. If that world were in our sky, the rings would span a width that makes the word magnificent seem shy. Over time, those rings may collapse into moons, a family forming before our eyes. Why parade these oddities through a story about life? Because context is the only honesty we have. If we only look for mirrors of Earth, we won't know when the universe is telling us something new. If we don't catalog the strange, we won't know which signals are truly special. And if we don't keep humility close, we will mistake surprise for proof. So how do we move from surprise to confidence with K2-18b? First, we keep measuring. You don't trust a single instrument, a single wavelength, or a single processing pipeline when the claim is this bold. You ask different cameras to watch the same eclipse. You read both the starlight filtering through the limb of the atmosphere during transit and the planet's own thermal glow when it slips behind the star. You build models that don't assume the answer you want, and you let rival teams try to break your result. If dimethyl sulfide is truly present in meaningful quantities, other gases should form a pattern around it: water and methane, carbon dioxide, and carbon monoxide in ratios that make sense. If the atmosphere is truly interacting with an ocean, certain species will be missing because the ocean eats them. It's the pattern that sells the story, not a single line in the spectrum. Second, we upgrade our playbook. Lab measurements of how molecules absorb light at the temperatures and pressures we expect, not at room temperature where it's convenient, can sharpen fingerprints and close loopholes. Better line lists turn ambiguous features into sharper choices. Haze physics, cloud microstructure, temperature gradients, every piece you refine removes a place where error can hide. Third, we stay honest about what 3 sigma means. It's an invitation, not a coronation. The same number that thrills a headline can shrink or grow with a different prior or a more realistic noise model. That doesn't mean the community is moving the goalposts. It means the game is hard. If all of this sounds like the slowest thriller ever written, remember what sits on the other end of patience. A universe with oceans that are not ours, breathing chemistry we can read. A nearby star with a planet that doesn't just reflect light, but tells us, molecule by molecule, what it's made of. If life has written itself into that air, even as a footnote, it will be the first time we have met biology without ever touching it. And if the signal weakens, if the data say, not this time, then the night doesn't get darker, it gets clearer. We'll know which false paths to stop following. We'll build better questions. The hunt sharpens. Now zoom out. The observable universe is about 93 billion light-years across, a number that makes the mind laugh and give up. In that enormity, one of the most compelling biosignature candidates rests only 124 light-years away. In cosmic distance math, that's next door. What are the odds that the first really promising hint would be that close unless hints are common? You don't need a crowded galaxy of civilizations to change the odds. You only need the realization that biology may be a habit of matter under the right conditions, not a miracle reserved for one pale dot. That doesn't solve the puzzle of the Great Silence. If life is common, why don't we hear civilizations calling? Maybe intelligence is rare. Maybe it blooms and burns too quickly. Maybe it hides on purpose. Maybe the distances between islands of mind are so huge that crossing them with signals is like throwing a whisper across a hurricane. None of those answers take away the wonder of a universe salted with simple life. If oceans full of microbes are scattered through the dark, the cosmos feels less like a void and more like a forest at night, alive but quiet. Here's a thought that keeps returning. When we finally confirm life elsewhere, it will change very little in our daily weather and very much in our weathered myths. The constellations will still rise, bills will still need paying, but the story we tell about ourselves will shift by a click. We will be one example, not the example. The privilege isn't lost, it's shared. So where do we stand with K2-18b? We have a signal consistent with a gas that, on Earth, is made by life. We have follow-up that made the case stronger, not settled. We have a debate that is loud because it matters, and cautious because the field remembers every time it got excited for the wrong reasons. We have upcoming observations that can either tighten the knot or allow it to slip. And we have a generation of instruments coming that will move beyond transit tricks to take direct spectra of nearby Earth-sized planets around small stars, pulling not just fingerprints, but portraits. Before those portraits arrive, the best thing we can do is learn how to be disciplined listeners. Build models that don't begin with the answer. Share data so rivals can try to break our darlings. Publish not just results, but caveats. Reward the teams that overturn their own claims. That's not the slow road. That's the only road that gets anywhere real. If you've stayed with me this far, you're part of a small group who actually wants the evidence and the nuance, not the sugar rush. You know that patience is not the opposite of passion. It's what happens when passion grows up. There's a quieter reason this search moves me. It isn't the promise of aliens with cities under two suns. It's the idea that life might be a conversation the universe keeps trying to have with itself. Chemistry becomes complexity. Complexity becomes curiosity. Curiosity builds tools that let it read chemistry far away and ask, "Are you there?" If K2-18b is breathing a gas made by living oceans, then the answer, after billions of years of silence, might be a whisper we can finally hear. And if not, the question is still beautiful. The hunt still worth it. We will point Webb again. We will tune our models again. We will listen again. Because somewhere in this vastness, a planet is exhaling a breath that did not exist before life arranged itself into something that eats and divides and dreams. When we find it, we will know not because someone says so, but because the evidence will corner us into agreement. Until then, let's promise each other something simple. We will follow the data wherever it leads. We will keep wonder and skepticism in the same hand. We will celebrate the almosts and learn from the not quites. And when the day comes that the spectrum is undeniable and the pattern of gases sings a chorus. Only biology knows how to sing. We will allow ourselves a very human thing, to feel less alone under the same sky we have always had. If this signal holds, Earth was never alone. Life would not be a single spark in a cold universe. It would be a constellation of fires lighting wherever conditions allow. The night will look the same, but it will not feel the same. The question, "Are we alone?" will stop being a wound and start being a measurement. Tonight, we learned how to take it a little better. This is Quantum Leap. If you want the evidence, not the hype, stay with us. We'll be here when the next spectrum lands. Whether it makes us cheer or makes us rethink. Either way, the story moves forward. Either way, the silence keeps cracking. And if you can feel it too, the sense that we are at the edge of the greatest revelation in human history, then you already know what to do. Hit subscribe so you don't miss the next step. Because somewhere out there, a planet is breathing, and we're finally learning how to listen.